Try to imagine nothing. Go ahead. Close your eyes and try to visualize absolute emptiness. You probably see a black void, maybe some stars in the distance if you're feeling romantic. But essentially, you picture a vacuum. You think of space as a stage, a big empty box where stuff happens. You put a planet here, a star there, maybe a confused astronaut floating in the middle. But the space itself, to you, it's just the container. It's the absence of things. I hate to break it to you, but that container doesn't exist. The idea of empty space is the greatest hallucination of the human mind. The universe isn't a box, it's a glob of jello. Okay, maybe not literal lime-flavored gelatin, but physically speaking, you are walking through a medium that is constantly being twisted, squashed, and pulled. When you look at the air in front of you, or the vacuum of space, you aren't looking at nothing. You are looking at a field. And until you understand what a field is, you don't understand physics. You're just memorizing rules for a game you don't know how to play. Let's start with something you can actually touch. Imagine a big, wobbling block of elastic material, a giant cube of jello sitting on a table. Now, suppose I reach in, grab a tiny speck of dirt trapped inside that jello, and I pull it. The jello distorts. It stretches. If you want to describe what happened to that block, you can't just say it moved. That's lazy. You have to describe how every single point inside that block shifted relative to every other point. We call this strain. If I pull the corner, the middle moves a little. The far side moves barely at all, and the point under my finger moves a lot. To describe this mess, we need numbers, a lot of numbers. For every tiny point in that jello, we need to know how much it stretched in the X direction, the Y direction, and the Z direction. And it gets worse. We need to know if it twisted. Did the top slide right while the bottom slid left? That's a shear. Suddenly, this innocent block of jello is a mathematical nightmare. To fully describe the stress and strain inside it, we can't just use a single arrow. We need a tensor, a beast of a mathematical object that packages all these stretches and twists together. But here's the beautiful part. This isn't just about jello. This is how the entire universe works. Physics is the business of assigning numbers to points in space. That's it. That's the job. If you assign a single number to every point in space, like, say, the temperature, you have a scalar field. Imagine a block of metal that's hot on one side and cold on the other. You can close your eyes and point to any spot inside that metal, and there is a specific number waiting for you, 20 degrees. Move an inch left, 25 degrees. The temperature doesn't jump around randomly, it changes smoothly. It forms a landscape. Now, imagine drawing lines connecting all the points that have the exact same temperature. You get these invisible surfaces, like the contour lines on a topographic map. We call them isotherms. They are imaginary, but they tell you the shape of the heat. But a single number isn't enough for the interesting stuff. Sometimes, the universe has an arrow at every point. Think about a rotating object, or water flowing in a river. At every single point in that river, the water has a speed, but it also has a direction. It's going somewhere. You can't just say, the water is moving at 5 miles per hour. You have to say, 5 miles per hour downstream. This is a vector field. Imagine the room you are sitting in right now. The air seems still, but it isn't. There are tiny currents everywhere. If you could freeze time and attach a tiny little red arrow to every molecule of air showing where it was going, the room would look like a porcupine. That forest of arrows is a field. Heat flow works the same way. Heat doesn't just sit there, it flows from the hot spots to the cold spots. So, superimposed over your scalar field of temperature numbers, there is a vector field of heat flow arrows. And here is the rule. The heat arrow always points downhill. It wants to get away from the hot zone as fast as possible. Now, we need a way to connect these two things, the temperature numbers and the flow arrows. How do we find out which way the heat will flow just by looking at the temperature map? We use a mathematical machine. We call it DEL, or Nabla, which is just a fancy name for an upside-down triangle symbol. But think of it as a meat grinder for function. You feed it the scalar field, the map of temperatures, and it chews it up and spits out a vector field. This operation is called the gradient, and it is exactly what it sounds like. If you are standing on a hillside in the pitch dark, and you want to know which way is up, you feel around with your feet. You find the direction where the slope is steepest. That direction is the gradient. The gradient of the temperature field is a vector that points in the direction of the hottest change. It tells you, if you want to get hotter, go that way. And the heat flow? It simply obeys the opposite of the gradient. It runs down the hill. But nature isn't satisfied with just flowing down hills. Sometimes nature likes to spin. Imagine you have a vector field that looks like a whirlpool. The arrows aren't flowing out from a center, they are circling around it. If you drop the leaf in there, it wouldn't just move, it would rotate. To measure this swirliness, we use another operation called the curl. If the gradient measures the slope of the hill, the curl measures how much the field is twisting. It tells you the rotation. And then there's the divergence. This measures how much the stuff is spreading out. If you have a nozzle spraying water, the divergence is high at the nozzle because water is exploding outward. If you have a drain, the divergence is negative because water is vanishing into it. Why am I telling you about hills, swirls, and drains? Because these three concepts, gradient, curl, and divergence, are the language of reality. Maxwell's equations, the laws that govern light, electricity, and your cell phone, are just sentences written in this language. They say things like, the divergence of the electric field is the charge. Electric charge is a sprayer that shoots electric field arrows outward. Or, the divergence of the magnetic field is zero. There are no magnetic sprayers, no magnetic charges. Magnetic lines never start or stop. They just loop forever. Speaking of magnetism, this is where things get really weird. You think you know what magnetism is. You played with magnets as a kid. You know they stick to the fridge and hate each other if you flip them around. But have you ever asked why? Why does a wire carrying an electric current suddenly turn into a magnet? Let's look at the Lorentz force. It's the rule that says if you shoot a charged particle through a magnetic field, it gets pushed sideways. Not forward, not backward, sideways. It's a force that acts perpendicular to the motion. That's bizarre. Gravity pulls you down. Electrical attraction pulls you closer. But magnetism pushes you sideways, like a rude pedestrian shoving you into traffic. The standard explanation involves the right-hand rule. You hold up your hand, point your thumb, curl your fingers, and look like you're trying to hail a taxi while doing yoga. It works, but it's arbitrary. Nature doesn't have hands. Here is the truth. Magnetism is not a separate thing. It's just electricity seen from a moving perspective. Imagine a copper wire. Inside, you have positive copper ions fixed in place and a sea of negative electrons flowing through them like a river. This is the current. Now imagine a single negative charge moving alongside this wire at the exact same speed as the electrons inside the wire. From your perspective, standing still in the lab, you see a current. You check your rule book and it says, currents create magnetic fields. Okay. The magnetic field pushes the moving charge toward the wire. Simple. But wait, let's look at it from the perspective of the moving charge. If you are the charge, you are looking at the electrons in the wire, and they look stationary relative to you because you're moving at the same speed. If they are stationary, there is no current. If there is no current, there is no magnetic field. So if there is no magnetic field, the force disappears, right? The charge should drift away? Wrong. The charge still gets pushed toward the wire. But how? If the magnetic force vanished, what is pushing it? Einstein steps in. You see, when things move, space itself contracts. It squishes. This is special relativity. From the perspective of our moving charge, the positive ions in the wire, which were stationary in the lab, are now rushing backward. Because they are moving, the distance between them shrinks. They get packed denser. Meanwhile, the electrons in the wire, which are moving with us, appear stationary. Their spacing relaxes. They spread out. Do you see what just happened? The wire, which used to be electrically neutral, now has a higher density of positive charges and a lower density of negative charges. To the moving particle, the wire has suddenly become positively charged. It's not magnetism pulling the particle in. It's good old-fashioned electric attraction. The particle sees a positively charged wire and wants to hug it. So what we call a magnetic field in the lab is just an electric field disguised by relativity. It's what happens to electricity when you start moving. This connects back to our vector field. We said earlier that fields define the force on a charge. We have an electric field vector, E, and a magnetic field vector, B. What we just discovered is that E and B aren't two different actors. They are the same actor, changing costumes depending on how fast you run past the stage. If you stand still, you see E. If you run, you see a mix of E and B. They are components of one giant four-dimensional object, the electromagnetic field. But there is a catch. To make this work, charge has to be indestructible. Think about the equation of continuity. It's a fancy way of saying charge is conserved. You can't create electrons out of nothing, and you can't make them vanish. If a current flows out of a box, the amount of charge inside the box must go down. It's basically accounting. If charge wasn't conserved, if it could change depending on your speed, the whole universe would break. Imagine heating up a block of metal. The electrons speed up. If their charge changed because of that speed, the block would suddenly become electrically charged just because it got hot. Massive sparks would fly every time you made toast. Since your toaster doesn't kill you, usually, we know charge is an invariant scalar. It's the same number no matter how fast you go. Now, let's go back to those magnetic field lines. Remember, divergence of B is 0. No magnetic charges. This means magnetic field lines have to form closed loops. They are like rubber bands that never break. If you have a straight wire, the field lines circle around it. If you have a loop of wire, the field lines thread through the middle and wrap around the outside, looking like a donut. This creates the magnetic dipole. It's the basic unit of magnetism. You don't have a north pole and a south pole sitting separately. You have a loop. The north is just the side where the lines come out, and the south is where they go in. But here is a question that should bother you. Where do the lines go when they hit the end of a bar magnet? They don't stop. They go through the magnet. A permanent magnet is just a solenoid that doesn't need a battery. Inside that iron bar, billions of tiny electrons are spinning. Each spinning electron is a tiny current loop. In iron, these loops decide to line up and sing in the same choir. The result is a macroscopic magnetic field. So there is no magic magnetic fluid inside the iron. It's just currents, permanent atomic currents that never stop flowing. But we are still describing this with lines and loops. Is that what's really there? Are there invisible spaghetti strings filling the room? Of course not. The lines are just a drawing tool. What's really there is the vector potential. And this is where we have to abandon the high school pictures entirely and look at the machinery under the floorboard. Because it turns out the magnetic field B might just be a derivative of something more fundamental, something we call A. We left off with a cliffhanger. We stripped away the magnetic field lines and realized they are just cartoons. We realized that magnetism and electricity are the same thing, just viewed from different speeds. But if we want to calculate this mess, if we want to actually predict what the universe will do next, we need to talk about the ghost in the machine. We need to talk about A. In electrostatics, life is easy. You have a scalar potential, voltage. It's like height on a topographic map. If you know the voltage everywhere, you just roll the ball down the hill, and that's your electric field. Simple.
But magnetism is a headache, because the magnetic field doesn't act like a hill. It acts like a whirlpool. It has a curl. So we can't represent it with a simple scalar number. We need a vector potential. We call it A. Think of A as the momentum of the field. If you have a flow of electric current, it drags the universe along with it. The current creates a river of this vector potential, flowing in the same direction. The magnetic field is just the swirl that happens around the edges of this flow. Now, is A real? Or is it just a mathematical trick to make our equations pretty? In classical physics, you can treat it as a trick. You can add any random value to A, and it doesn't change the physical magnetic field at all, just like changing sea level doesn't change the steepness of a mountain. But in more advanced physics, quantum mechanics, this ghost field turns out to be the main character. It's the thing that actually matters. If you don't like ghosts, you can do it the hard way. You can calculate the magnetic field directly from the currents using a beast of a formula called the Biot-Savart law. Imagine breaking a wire into infinite tiny pieces.
Each little piece of current screams out a magnetic command to the rest of the universe. The Biot-Savart law is just the sum of all those screams. It's a messy calculation involving cross products and inverse squares, but it tells us something profound. The field at any point is the sum of the influences of every moving charge in the universe, weighted by distance. This leads us to the dipole, the fundamental atom of magnetism. Since we can't have magnetic charges, the smallest magnetic object is a tiny loop of current. Far away from a complicated mess of wires, everything starts to look like a simple dipole. It doesn't matter if your current loop is a square, a circle, or a triangle. From a distance, the universe doesn't care about the shape. It only cares about the magnetic moment, the current times the area. This is why atoms, with their spinning electrons, behave like tiny bar magnets. They are microscopic loops. Now, I want to pivot. We've been talking about fields as if they are these ethereal, magical clouds. But to truly understand the vacuum, you need to think of it as a solid object. You need to think about Jell-O again. When we study the mechanics of solid materials, elasticity, we find the exact same mathematics that governs the vacuum of space. Consider a glob of Jell-O that is twisted and squashed. To describe the internal state of that Jell-O, we can't just say it's under pressure. Pressure is a scalar. It pushes everywhere equally. But in a solid, you can push on one face and pull on another. You can shear it. We describe this internal torture with a stress tensor. It's not a single number. It's a matrix of forces. It tells you the force in the x direction on the face perpendicular to the y-axis, and so on. And how does the material respond? It deforms. We call this strain. If a point inside the material moves, we describe that displacement with a vector. The strain isn't just the displacement, it's the change in displacement from one point to the next. It's the stretching and the twisting. This is defined by the strain tensor. This tensor has 6 independent numbers that tell you exactly how every patch of space is being warped. Why am I talking about Jell-O in a physics script? Because energy doesn't care what it's made of. When you squeeze a spring, you store energy. When you shear a block of metal, you store energy. The amount of energy stored depends on the product of the stress, how hard you push, and the strain, how much it moves. This is true for the vacuum of space, too. An electric field is a stress. A magnetic field is a stress. The empty space between stars is loaded with potential energy, stored in the electromagnetic fields just like energy is stored in a twisted rubber band.
If you understand Hooke's law, that stress is proportional to strain, you understand the basic machinery of existence. In a solid, if you kick it, a wave travels through it. We call it sound. The speed of that sound depends on how stiff the material is and how heavy it is. In the vacuum, if you kick the electromagnetic field, a wave travels through it. We call it light. The speed of light is determined by the stiffness of the vacuum, just like the speed of sound is determined by the stiffness of a rock. But here is where the analogy gets fun. Materials aren't perfect. If you pull a spring too hard, it snaps. If you take a piece of chalk and pull the ends, it breaks. But notice how it breaks. It snaps perpendicular to the pull. Why? Because chalk is weak in tension. It can't handle being pulled apart. But if you twist the chalk, it breaks in a spiral at a 45-degree angle. Why? Because twisting creates a shear, but that shear is mathematically equivalent to a tension at a 45-degree angle. The chalk still breaks in tension, but the geometry of the twist hides where the tension is. Nature is full of these hidden mechanisms. Materials like plastic film behave even stranger. You crumple it, and it slowly unfolds. It remembers its shape. It has internal viscosity, fluids moving between cells, that fights the restoration. The vacuum of space doesn't seem to have a breaking point or viscosity in the same way, but the math of tensors, the stress and the strain, is the language we use to describe gravity and the curvature of space-time itself. Einstein didn't invent a new language. He borrowed the language of geology and engineering. He treated the universe like a giant, bendable solid. So, what is the quantum vacuum? It is not empty space. It is a medium.
It is a playground of fields described by vectors, scalars, and tensors. It has a temperature field. It has a heat flow vector. It has electric and magnetic stresses. It has a vector potential that guides the flow of reality. Understanding physics isn't about memorizing the formula for the magnetic field of a solenoid. It's about having a feel for the field lines. It's about understanding that a differential equation isn't just algebra. It's a set of instructions for how the universe changes from 1 millimeter to the next. As Dirac said, you only understand an equation if you can guess the answer without solving it. You need to visualize the invisible. So, the next time you look at the night sky, don't see emptiness. See the fields. See the tensors stretching and squeezing. See the huge invisible ocean of vector potential swirling around every wire and every atom. The universe is a crowded place, my friends, and the nothing is the heaviest thing in it. If you enjoyed having your perception of reality twisted like a piece of chalk, hit that like button. Let me know in the comments if you want to dive deeper into the tensors that hold the universe together.
Have you ever finished reading a page, reached the end, and realized you have absolutely no idea what you just read? Your eyes moved across the words. You saw them. But somehow, nothing stayed. It's as if the information just passed through your mind like water through a sieve. This is one of the most frustrating experiences in learning. We read something important, something we need to know, and a day later it's gone. A week later, we might as well have never read it at all. So what's happening here? Why does our brain seem to let so much slip away? The answer isn't that we have bad memory. The problem is that we've misunderstood what memory actually is and how it works. Most people treat their brain like a recording device, like a camera that's supposed to capture everything it sees. But that's not how it functions, not even close. Think about the last time you walked through your house. You saw the furniture, the walls, the doors. But right now, could you describe the exact pattern of wear on your doorknob? Or the precise number of books on your shelf? You saw these things, but you didn't encode them. Your brain didn't store them because it didn't think they mattered. This is the first thing to understand. Your brain is not trying to remember everything. It's trying to remember what's important, and it decides what's important based on very specific signals. If we want to remember what we read, we need to understand these signals and work with them, not against them. Let's start with what actually happens when you read something. The words come in through your eyes. They get processed in the visual cortex. Then they're converted into meaning in the language centers of your brain. But here's the critical part. Just because information reaches your brain doesn't mean it gets stored there. It's like the difference between someone telling you something and you actually writing it down. The information was present, but was it recorded? Memory formation requires something more than just exposure. It requires encoding, and encoding doesn't happen automatically. It happens when your brain decides that the information is worth the energy it takes to store it. Because make no mistake, remembering things costs energy. Maintaining neural connections, strengthening synapses, integrating new information with old information, all of this requires resources. So your brain is selective. Think of it this way. Imagine you walking through fresh snow. The first time you take a path, you leave footprints, but they're shallow. If it snows again, those footprints disappear. But if you walk the same path every day, eventually you create a clear trail. The snow gets packed down, the path becomes obvious. That's what happens with memory. A single exposure creates a faint trace, but repetition, and more importantly, engagement with the material, packs that path down. But here's where it gets interesting. Not all repetition is equal. You could read the same page 10 times passively, letting your eyes glide over the words, and still remember almost nothing. Why? Because your brain isn't interpreting passive reading as a signal that this information matters. There's no struggle, no effort, no connection being made. It's like walking the same path in the snow but stepping in slightly different places each time. You never reinforce the same trail. So what does work? What makes information stick? The answer lies in something called elaborative encoding. This is the process of connecting new information to things you already know, of transforming abstract concepts into concrete examples, of asking questions about what you're reading rather than just absorbing it. Let's say you're reading about how the heart pumps blood. If you just read the heart has 4 chambers and valves that prevent backflow, that's one kind of learning. It's abstract. It's isolated. But if you stop and think, wait, why 4 chambers? Why not 2 or 6? And these valves, they're like the check valves in plumbing that keep water from flowing backward. Now you're doing something different. You're connecting the new information to something you already understand. You're asking why things are the way they are. You're building mental models. This is what makes information memorable. Not repetition alone, but meaningful processing. Your brain stores things that it has worked with, manipulated, questioned, and connected. It's the difference between hearing a phone number once and dialing a phone number. When you dial it, you have to actively recall each digit, place it in sequence, and execute an action. That active retrieval is what creates strong memory traces. There's a principle in neuroscience called the generation effect. It shows that information we generate ourselves is remembered better than information we simply read. If you read a sentence like "the hungry man ate the pizza," you'll remember it somewhat. But if you read "the hungry man ate the" and have to supply the word yourself, you'll remember it much better. Why? Because generation requires retrieval. It requires you to search your memory, to activate related concepts, to create something rather than just receive it. This is why summarizing what you read in your own words is so powerful. When you close the book and try to explain the concept to yourself, you're forcing your brain to reconstruct the information from memory. And that reconstruction process, that's what creates strong, lasting memories. Every time you successfully retrieve something, you're strengthening the path to it. Now, there's another crucial element: understanding. True understanding creates memory almost automatically. Think about the difference between memorizing a series of random numbers and understanding why those numbers form a pattern. Random numbers are hard to remember because there's no structure, no meaning. But if you understand that the numbers are the Fibonacci sequence, where each number is the sum of the two before it, suddenly they're easy. You don't need to memorize each individual number because you understand the rule that generates them. This is why reading for understanding, not just for exposure, is so important. When you understand something deeply, when you grasp not just what happens, but why it happens, you're creating a compressed representation in your mind. Instead of storing 1,000 individual facts, you're storing the underlying principle that generates those facts. It's vastly more efficient. Consider how you remember stories versus how you remember lists. Stories are easy to remember because they have structure, cause and effect, character motivation, sequences that make sense. Lists are hard because they're arbitrary. There's no inherent connection between item 1 and item 2. This tells us something important. Our memory is designed for meaning, not for arbitrary information. So when you're reading, especially something dense or technical, the key is to constantly search for the meaning. Don't just read what happens, ask why it happened. Don't just accept a statement, think about what it implies. Does this new piece of information contradict something you thought before? Does it explain something you've been confused about? Does it connect to something in a completely different domain? These questions aren't extra work on top of reading. They are the work. They're what transforms reading from a passive activity into an active one. And active processing is what creates memory. There's also the matter of timing. Our brains consolidate memories in phases. When you first read something, it exists in what we call working memory. This is temporary, like RAM in a computer. It holds information just long enough for you to use it. But for information to move into long-term storage, it needs to be consolidated. And consolidation takes time. This is why cramming doesn't work well. You can shove information into working memory right before a test, and it might be there when you need it, but a week later, it's gone. It never got properly consolidated. The information never made it from that temporary storage into the stable, long-term networks of your brain. What does work is spaced repetition. Instead of reading something once for an hour, you're better off reading it for 20 minutes, then coming back to it tomorrow, then again in 3 days, then again in a week. Each time you return to the material, you're forcing your brain to retrieve it, and retrieval is what strengthens memory. The spacing gives your brain time to consolidate between sessions. But here's what makes this even more effective. Each time you come back, don't just reread. Test yourself. Try to recall the main points before you look at them again. This retrieval practice is one of the most powerful learning techniques we know of. It feels harder than just rereading. It's supposed to. That difficulty is the signal your brain needs to recognize that this information is important. Think about learning to ride a bicycle. You can watch videos of people riding bikes. You can read about balance and momentum, but you won't learn until you actually get on the bike and struggle with it. The struggle, the wobbling, the near falls, these aren't obstacles to learning. They are learning. Your brain learns by doing, by failing, by correcting. The same is true for intellectual learning. The struggle to recall, the effort to reconstruct, the work of generating answers. This is what creates lasting memory. Now, let's talk about something subtle but important. Context and cues. Memories aren't stored in isolation. They're stored in networks connected to all sorts of contextual information. Where were you when you learned something? What were you thinking about? What else was happening? All of these become cues that can trigger the memory later. This is why it's easier to remember something in the same environment where you learned it. The room, the lighting, even the smell, these all become associated with the memory. But here's the problem. If you only study in one place, your memory becomes dependent on those cues. And when you need to recall the information somewhere else, it's harder. The solution is to vary your learning environment. Read in different places. Review material in different contexts. This forces your brain to encode the information more abstractly, less tied to specific cues. It makes the memory more flexible, more robust, more accessible from different mental states. There's also the question of depth. You can read something at a surface level, understanding the basic gist, or you can read it deeply, wrestling with implications and connections. Deep processing creates stronger memories. It's the difference between recognizing a face and knowing a person. Recognition is shallow, you know you've seen them before. Knowing is deep, you understand their personality, their history, their quirks. When you read, aim for knowing, not just recognizing. This means pausing frequently. It means asking questions. What's the author really saying here? Why is this point important? How does this relate to what came before? Could this be explained differently? Do you agree with this? Why or why not? These questions might slow down your reading speed, but they dramatically increase what you retain. And here's something interesting. Over time, as you get better at this kind of active reading, it doesn't slow you down as much. You develop the skill of reading and thinking simultaneously. The questioning becomes automatic. You start to notice patterns more quickly, make connections more easily. Your understanding accelerates. Let's consider one more aspect, the role of emotion. We remember things better when they're emotionally significant. A dramatic story sticks more than a dry recitation of facts. Why? Because emotion is one of the brain signals that something matters. When you feel something, curiosity, surprise, confusion, excitement, your brain pays more attention. It encodes more deeply. This doesn't mean you need to artificially manufacture emotion while reading, but it does mean that staying engaged, staying curious, allowing yourself to be surprised or puzzled, these states facilitate memory. If you're bored, if you're just going through the motions, your brain interprets that as a signal that this information isn't important. It allocates fewer resources to encoding it. So if you find yourself bored while reading something you need to remember, that's a problem to solve, not just a mood to tolerate. Can you approach the material differently? Can you find a question within it that genuinely interests you? Can you look for connections to something you do care about? Sometimes the key to remembering isn't technique, it's finding a way to genuinely engage with the material. All of this points to a central truth about memory. It's not a passive recording, it's an active reconstruction. Every time you remember something, you're rebuilding it from pieces. And the act of rebuilding it changes it slightly, strengthens certain connections, weakens others. Your memory is alive, dynamic, constantly being reshaped by how you use it. This means that the best way to remember what you read is to use it, write about it, explain it to someone else, apply it to a problem you're trying to solve. Think about how it changes what you believed before. Let it interact with other things, Every time you actively work with the information, you're strengthening it, integrating it more deeply into your web of knowledge. The person who reads a book and then closes it, moving on to the next thing, will forget most of it. The person who reads a book and then spends time thinking about it, discussing it, applying its ideas, will remember it for years. The difference isn't in the reading itself, it's in what happens after. Here's the beautiful part. Once you understand how memory works, you stop fighting against your brain. You work with it. You recognize that forgetting is natural and expected when you don't give your brain the signals it needs. You understand that difficulty during learning isn't a sign you're doing something wrong. It's often a sign you're doing something right. That struggle to recall, that effort to connect ideas, that work of generating rather than just receiving, this is what builds lasting knowledge. Memory isn't about having a better brain. It's about using your brain the way it's designed to be used. And it's designed for meaning, for connection, for active engagement. Give it those things and you'll be amazed at what stays with you. Not because you have a special gift, but because you're working with the natural mechanisms of how learning happens. The next time you pick up something to read, something you want to remember, don't just read it. Engage with it, question it, connect it, reconstruct it in your own words. Come back to it, test yourself on it. Let it change how you think about other things. Treat reading not as a task to complete, but as a conversation to have with ideas. Do this, and you won't need tricks and mnemonics for most of what you read. Understanding itself will be your memory. The ideas will stick not because you forced them to, but because they became part of how you think. And that's not just better memory. That's actual learning.
When people hear the word mass, they usually think of heaviness. Something massive feels difficult to lift, difficult to move, difficult to stop. That intuition points in the right direction. But in physics, mass plays a more precise role than everyday language suggests. Mass is about resistance to change in motion. Push an empty shopping cart and it responds immediately. Load it with groceries and the same push produces a much smaller effect. Nothing about the push changed. Nothing about the floor changed. What changed was the amount of mass that had to be persuaded to move differently than it was moving before. Mass measures how strongly matter resists acceleration. This resistance appears in every situation where motion changes. Starting to move, stopping, turning, or speeding up all require effort when mass is involved. The greater the mass, the more effort is required to produce the same change. Once an object with mass is moving, it does not easily give up that motion. Once it is at rest, it does not easily begin moving. Motion demands a cause, and mass determines how large that cause must be. This already tells us something important. Mass does not describe how fast something moves. Two objects can travel side by side at the same speed and respond very differently when pushed. Mass cares about change, not motion itself. Now gravity enters the picture, and everyday experience begins to blur ideas together. On Earth, objects with more mass feel heavier because gravity pulls on mass. More mass means a stronger gravitational pull, which we experience as greater weight. Because gravity is always present in daily life, mass and weight often get treated as the same thing. Physics keeps them distinct. Mass belongs to the object itself. Weight belongs to the interaction between that object and a gravitational field. Take the same object to the moon, and the weight decreases. The mass does not. The resistance to acceleration remains exactly the same. This separation matters because gravity is only one way mass reveals itself. There is a deeper fact hiding here. The quantity that determines how strongly gravity pulls on an object is exactly the same quantity that determines how strongly that object resists acceleration. Experiments show this equivalence with extraordinary precision. No adjustments are needed. The numbers match every time. Because of this, mass links motion and gravity into a single concept. It sets the scale for how objects respond to forces and how they influence one another. Wherever mass appears, it defines how difficult change will be. Without announcing itself, mass shapes how the physical world behaves. And once you accept that mass measures resistance to change, the picture widens in an unexpected way. Up to now, mass has sounded like a property objects carry around with them, something internal, something local. But mass does more than resist acceleration. It also participates in the structure of the universe itself. To see this, forget objects for a moment and think about motion in empty space. If there were no mass anywhere, space and time would behave like a simple grid. Straight lines would stay straight. Clocks would tick the same way everywhere. Motion would follow predictable paths, unless something intervened. Introduce mass, and that picture no longer holds. Mass affects how objects move, not only by responding to forces, but by influencing the very arena in which motion takes place. In modern physics, space and time are not separate backgrounds where events happen. They are joined into a single structure called space-time, and mass plays a central role in how that structure behaves. This sounds abstract, so let's ground it. Imagine two nearby clocks, one placed on the ground and one lifted higher. Even before worrying about motion, they do not measure time the same way. The clock closer to a massive object runs differently from the one farther away. This difference is not a malfunction, it is a physical effect. Time itself depends on the presence of mass. The same happens with distance. Straight paths bend near massive objects. Light, which has no mass of its own, still follows curved routes when it passes near large masses. Nothing pushes it sideways, it simply follows the geometry shaped by mass. Mass does not pull on space and time like a hand tugging on fabric. Instead, mass and energy determine how space-time is arranged, and objects move according to that arrangement. Motion follows the available geometry. This is why gravity looks the way it does. Rather than thinking of gravity as a force acting at a distance, physics treats it as the result of mass influencing space-time and objects moving accordingly. A planet orbiting a star is not being dragged around by an invisible tether. It is following the most natural path available in the space-time shaped by the star's mass. This explains something that once seemed mysterious. Objects fall at the same rate, regardless of their mass, as long as other effects are negligible. The resistance to acceleration and the gravitational influence scale together. Because of that balance, motion under gravity becomes independent of the object's own mass. Mass shapes space-time. Objects respond to space-time. The result is what we experience as gravity. Now pause and connect this back to the earlier idea of resistance to change. An object with mass resists changes in motion. Space-time with mass resists being arranged in a flat, uniform way. In both cases, mass introduces rigidity. It sets how difficult it is for motion and geometry to behave differently than they already do. This brings us to an important point that often causes confusion. Mass is not the same as energy, but they are closely related. Energy contributes to space-time in much the same way mass does. Heat, motion, and radiation all influence space-time, though mass tends to dominate in everyday situations because it is concentrated. That famous equation connecting mass and energy is not about explosions or technology. It is a statement that mass is one way energy can exist, and that energy, in any form, participates in shaping space-time. So mass is no longer just about heaviness or resistance. It becomes part of the reason space and time behave the way they do. At this stage, it helps to let go of the idea that space-time is a thing sitting underneath the universe. It behaves more like a set of relationships, how distances are measured, how durations pass, how paths are traced. Mass influences those relationships directly, and this influence is not optional. You cannot turn it off. Any amount of mass, no matter how small, contributes. The effects only become noticeable when the mass is large or concentrated enough, but the rule applies everywhere. What began as a measure of how hard it is to push something now reveals itself as a measure of how strongly matter participates in the structure of reality. Mass tells space-time how to behave, and space-time tells matter how to move. Once you see that connection, mass stops being a simple property of objects and becomes a key player in the architecture of the universe. And once mass is seen as something that participates in space-time itself, another question becomes unavoidable. Where does mass come from? Up to this point, mass has behaved like a given. Objects have it. It resists acceleration. It influences space-time. But physics does not stop at description. It keeps asking, what mechanisms make those descriptions true? Here is the surprising answer. Most of the mass you encounter every day does not come from the intrinsic mass of particles. Take a proton, one of the building blocks of atomic nuclei. It is made of quarks, and quarks do have mass. But if you add up the masses of the quarks inside a proton, you get only a small fraction of the proton's total mass. The majority comes from something else entirely. It comes from energy. Inside the proton, quarks move at enormous speeds and interact through strong forces. The energy stored in that motion and interaction contributes to the proton's mass. According to the rules of physics, energy and mass are deeply linked, so confined energy shows up as mass. This means that much of what you call matter is energy held in place by interactions. Mass, in practice, measures how much energy is tied up in a system in a way that resists change. This idea scales upward. The mass of everyday objects comes largely from the mass of protons and neutrons, which themselves owe most of their mass to internal energy. Even solidity, the feeling that objects are rigid and substantial, comes from electromagnetic interactions between atoms, not from mass alone. Mass is not a simple substance filling space. It is an expression of how energy is organized and constrained. Now this leads directly to another common confusion. If energy can appear as mass, and mass influences space-time, does that mean mass and energy are the same thing? Not exactly. They are different ways of describing the same physical content depending on context. When energy is localized and behaves like inertia, we describe it as mass. When it moves freely or spreads, we describe it as energy. The distinction is practical, not fundamental. This explains why light, which has no mass, still carries energy and momentum and can influence space-time. It does not resist acceleration in the same way matter does, but it still participates in the overall structure. Mass becomes a special case, energy that is bound in such a way that it resists changes in motion and position. Now return to inertia, the resistance to acceleration that started this discussion. In classical physics, inertia simply exists. Objects resist acceleration because they do. Modern physics digs deeper and asks what gives particles that resistance in the first place. Here another piece enters the picture: fields. Particles do not exist in isolation. They exist in the presence of fields that fill space. One of these fields plays a special role in determining mass. Interaction with this field gives certain particles their intrinsic mass. Without that interaction, many particles would behave as if they were massless, moving at the speed of light. Mass, at the most basic level we know, emerges from interaction, not isolation. This reinforces a theme that keeps appearing. Mass is relational. It expresses how strongly something is tied into the rest of the physical world. The more tightly energy is bound, or the more strongly a particle interacts with relevant fields, the more mass it exhibits. Mass is not a label attached to matter. It is a measure of participation. Now consider how this affects motion at very high speeds. As objects move faster, changing their motion becomes increasingly difficult. Adding the same amount of energy produces smaller changes in speed. This is not because the object is gaining mass in a literal sense, but because space-time itself imposes limits on how motion can change. The resistance to acceleration increases as speed approaches the maximum allowed speed. Once again, mass and space-time work together. What begins as inertia at low speeds becomes a geometric constraint at high speeds. This shows that mass is deeply connected to limits. Limits on acceleration, limits on energy concentration, limits on how space-time responds, and limits are often where understanding becomes sharpest. Now bring all of this back to scale. At small scales, mass arises from particle interactions and confined energy. At human scales, it governs how objects respond to forces and gravity. At cosmic scales, it shapes space-time and determines how galaxies form, how stars orbit, and how light travels across the universe. The same concept applies everywhere, only the language changes. This universality is what makes mass such a powerful idea. It appears in mechanics, thermodynamics, quantum theory, and relativity without changing its role. The equations look different, but the meaning persists. Mass measures how strongly something resists change and how strongly it influences the structure around it. And this brings us to an important correction to everyday intuition. Mass does not make things want to stay still. Objects do not prefer rest. Motion and rest are relative concepts. What mass does is resist changes in motion, regardless of the current state. Rest and uniform motion are treated the same by physics. This is why astronauts floating in space still have mass. They are weightless, not massless. They resist being pushed just as much as they would on Earth. The absence of weight does not remove inertia. Weight is local, mass is universal. Once this distinction is fully absorbed, many confusions dissolve. Falling objects, orbiting planets, floating astronauts, and bending light all follow from the same idea applied in different settings. Mass becomes less mysterious, not more. It is no longer a substance hidden inside matter. It is a measure of how matter and energy respond to the rules of motion and space-time. And with that understanding in place, mass stops being a word you memorize and becomes a concept you can use. one that explains why the universe reacts the way it does whenever anything tries to change. And at this point, mass can finally be treated as a fully connected idea rather than a collection of separate facts. Mass is not just resistance to acceleration. It is not just what gravity acts on. It is not just a number listed next to particles in a table. Mass is the quantity that ties together motion, gravity, energy, and space-time into a single framework that works at every scale we can test. When physicists use mass in an equation, they are not inserting a vague property. They are specifying how strongly a system resists changes in motion, how much it contributes to space-time geometry, and how much energy is locked into a form that behaves inertially. One number plays all of these roles because experiments show they are inseparable. This is why mass appears in so many places without changing meaning. In mechanics, it sets how force produces acceleration. In gravity, it determines how objects influence one another's motion. In relativity, it contributes to how space-time is shaped. In particle physics, it reflects how particles interact with underlying fields. Different theories, same role. Mass is consistent across contexts. That consistency allows physicists to trust it. When calculations involving mass agree across experiments as different as particle collisions, planetary motion, and atomic measurements, the concept earns its place as fundamental. It also explains why mass cannot be defined in isolation. You cannot measure mass without interaction. You measure it by pushing, pulling, colliding, orbiting, or observing motion under gravity. Mass reveals itself only through relationships. It is not a private attribute of an object. It is how that object participates in physical processes. This relational nature becomes especially clear when mass is absent. Particles with no mass still carry energy and momentum, but they do not resist acceleration in the same way. They cannot be brought to rest. Their behavior marks the boundary of what mass changes. Comparing massive and massless systems highlights exactly what mass contributes and what it does not. Mass introduces inertia. Mass introduces gravitational influence. Mass introduces limits on how motion responds to added energy. Remove mass and those features disappear. At the same time, mass does not act alone. Energy, momentum, and space-time geometry work together. No single concept explains everything. Mass matters because it connects these ideas in a way that remains valid whether you are studying atoms, engines, planets, or galaxies. This is also why mass is not something physics expects to be replaced or discarded. Future theories may explain its origin more deeply or describe it in new language, but they will still need a quantity that plays the same role. Whatever name it goes by, it will have to resist acceleration, contribute to gravity, and participate in space-time. Those requirements are not optional. They come directly from observation. So when someone understands mass in physics, they are not just learning a definition. They are learning how physicists think about change. They learn why motion responds the way it does, why gravity behaves universally, and why energy cannot be rearranged without consequences. Mass becomes a practical tool for reasoning. It allows you to explain why heavy and light objects respond differently to forces, why astronauts float yet still resist pushes, why stars bend the paths of light, and why most of the matter around you owes its mass to energy bound by interactions rather than to tiny particles acting alone. Once mass is understood this way, it stops being confusing. It becomes predictable. It becomes something you can explain without memorizing phrases or relying on vague analogies. Mass is how physics keeps track of resistance to change and influence on space-time, using one quantity that works everywhere it is applied. And that is why mass remains one of the central concepts in physics, not because it is mysterious, but because it is reliable.
You are completely wrong about time. You probably think you know what it is because you look at a watch or you feel yourself getting older. But that isn't time. That's just a sensation, a biological trick. Most people walk around with this poetic idea in their heads that time is a river. You imagine it flows, sweeping you along from the past, through the present, and into the future. You think it moves. But here is the problem with that beautiful image. If time is a river, how fast does the river flow? 1 second per second? That is meaningless. That's like saying a table is 1 table long. It tells you absolutely nothing about the nature of reality. The truth is much stranger, much more mechanical, and honestly, a lot less romantic than a flowing stream. Time doesn't flow. Time doesn't push you anywhere. And if you think you have a good grip on how time works, just because you can count seconds in your head, you are in for a very rude awakening. Let's start with what goes on inside your brain, because that is where the confusion begins. You think your internal clock is a reliable instrument. It isn't. It is a chaotic mess of translation schemes. Consider a simple experiment. Try to count to 60 seconds in your head. Just sit there and count. 1, 2, 3. You think you are tracking time, but what you are really doing is running a very specific, very personal program. Some of you, when you count, you hear a voice in your head. You are literally speaking to yourself, sub-vocalizing 1, 2, 3. If someone interrupts you and asks you to speak, you lose your count. The machine jams. But others, and this is where it gets interesting, don't hear a voice at all. They see images. They might see a tape measure with numbers on it, clicking past like a ticker tape. Clink, clink, clink. If you use that visual tape measure system, you can actually read a newspaper or check a laundry list while you count time. You can sort your socks, look at patterns in the weaving, and still keep that mental tape measure clicking perfectly. But the person who counts with a voice, they can't read a word without losing track of the time. This tells us something fundamental. What you experience as the passage of time is just a mental construct, a pattern-matching game your brain plays. It varies wildly from person to person. It is not a universal constant. It is a biological hallucination. So, when we talk about physics, when we talk about the universe, we have to throw your brain out the window. We have to stop talking about how it feels and start talking about what it actually is. In physics, we have to be operational. That means we don't ask, what is the essence of time? Because that is a question for philosophers who enjoy arguing over coffee. We ask, how do we measure it? And the answer is almost disappointingly simple. Time is just a way of ordering events. That's it. It is a labeling system. Imagine you have a deck of cards. You lay them out in a row. You can say the jack is before the queen and the king is after the queen. The cards aren't moving. The table isn't flowing. The order is just a structural property of how the cards are arranged. Time is the table. Events are the cards. When we say time passes, we are just reading the cards from left to right. This brings us to the biggest mistake everyone makes. You think time is a container. You imagine the universe is a big empty box, and time is a clock on the wall of that box, ticking away even if the box is empty. You think that if we removed all the stars, all the planets, all the atoms, and all the light, time would keep ticking. Tick, tick, tick. Wrong. This is the Newtonian view, and it is dead. Time is not a background stage. Time is a measure of change. If absolutely nothing in the universe changes, no atoms vibrate, no light moves, no energy shifts, then time stops. It ceases to have meaning. You cannot define a second without a physical process to mark it. A swinging pendulum, a vibrating quartz crystal, a cesium atom oscillating. Time is not separate from the stuff in the universe. Time is a property of the stuff. This is where your intuition fights back. You say, okay, but surely time acts on things. Time makes me get older. Time causes the milk to spoil. No, it doesn't. This is a linguistic trap. Time is not an agent. Time doesn't have hands. It doesn't reach into the fridge and sour your milk. Bacteria do that. Chemical reactions do that. Entropy does that.
Time is just the bookkeeping system we use to track the rate at which those reactions happen. Saying time did it is like saying inches built the house. Inches didn't build anything. Carpenters, inches just tell you where the walls are. Time is the ruler, not the worker. Let's push this ruler analogy further because this is where things get really weird. If time is just a ruler we use to measure the distance between events, what happens if the ruler itself is flexible? This isn't science fiction. This is measurable fact. We used to think that a second was a second, anywhere in the universe. If you had a clock on Earth and a clock on Mars, they would tick-tock in perfect unison. It feels obvious, it feels right, and it is completely false. The rate at which clocks tick depends on where they are and how fast they are moving. This is not a mechanical failure of the clock. It is a fundamental feature of reality. Imagine you are driving a car across a giant flat sheet of paper. You can drive north or you can drive east. If you drive purely north, you are making maximum progress in the northward direction. But if you turn the steering wheel and start driving northeast, you are sharing your speed. You are moving a bit north and a bit east. You aren't going north as fast as you were before because you diverted some of that motion to the east. Now, replace north with time and east with space. This is the essence of relativity. You are always moving through the universe at a constant speed, but that motion is shared between space and time. If you sit perfectly still in your chair, you are dedicating all your motion to moving through time. You are traveling into the future at maximum speed, 1 second per second. But the moment you stand up and walk, or get in a rocket and fly, you are diverting some of that motion into space. You are moving through space, which means you must, mathematically must, move slower through time. Your clock slows down. Your aging slows down. You aren't breaking the machine. You are just changing direction on the map. If you could move at the speed of light, which is the maximum speed limit of the universe, you would be using 100% of your motion for space. You would have zero motion left for time. For a photon of light, time does not pass. It is born and absorbed in the same instant of its own perspective. The universe is frozen. Now, you might be thinking, well, I don't feel my watch slowing down when I run for the bus. Of course not. You are too slow. You are a biological snail. The effects are tiny at human speeds, but they are real. We have to program satellites with this math. Satellites are moving fast, so their time is different from your time. We literally have to adjust their clock motion. There is another aspect of time that tricks us, and it comes back to that counting socks problem, the idea of pattern recognition. We perceive time as having a direction, an arrow. Past is fixed, future is open. You can remember breakfast, but you can't remember dinner. Why? If physics equations work forwards and backwards, and most of them do, why can't we remember the future? If you film a planet orbiting a star and play it backward, it looks perfectly fine. It obeys all the laws of gravity. But if you film an egg falling on the floor and breaking, and then play it backward, everyone knows it's fake. The yellow yolk doesn't leap off the floor, assemble itself into a ball, and seal itself inside a shell. Here's the secret. This isn't about time itself. It's about probability. It's about disorder. It is much, much easier to break an egg than to build one. There are a billion ways for an egg to be broken. Scattered here, splattered there, shell in 3 pieces, shell in 1,000 pieces. But there is only one specific arrangement where the egg is whole. So, as things move and interact, they naturally stumble from the organized state, few options, to the disorganized state, many options. We call this entropy, and this is the only reason you feel an arrow of time. You are watching the universe shuffle the deck of cards. You started with a perfectly ordered deck, and every second that ticks by is just the universe shuffling it a bit more. You can't unshuffle the deck just by hoping. This means that your sensation of time flowing is actually just your brain registering the increase of messiness in the universe. You are a disorder detector. When you distinguish the past from the future, you are really just distinguishing less messy from more messy. If the universe were in a state of maximum mess, maximum entropy, where everything was evenly spread out and nothing interesting was happening, your brain wouldn't be able to tell the past from the future. There would be no egg to break. There would be no memory to form. In a thermal equilibrium universe, the arrow of time vanishes. So, let's go back to those people counting in their heads. The ones seeing the tape measure versus the ones hearing the voice. They are both struggling to impose a rigid linear structure on a universe that is actually much more flexible. We build these mental models, these counting machines, because we need to survive. We need to know when the tiger is coming or when the harvest is ready. We evolved to track duration, but we did not evolve to understand the dimension of time. Our brains are efficient, not accurate. We focus on the now because that is where we live. But in physics, now is a very slippery concept. If you and I are standing next to each other, our now is effectively the same. But if you are on a planet 1,000,000 light years away and you start walking away from me, your definition of now slices through the universe at a different angle than mine. What you consider to be happening right now might be in my future. What I consider right now might be in your past. There is no universal now that covers the whole universe like a blanket. The universe is a block of events, a four-dimensional loaf of bread, and how you slice that loaf depends on how fast you are moving. This is hard to grasp. It feels wrong. It feels like I'm telling you that up is down, but that is because you are trying to translate the high-level language of the universe into the low-level language of your biology. You are trying to count socks when you should be measuring light beam. When you try to force the universe to fit your intuition, you get confusion, you get paradoxes. But when you let go of what you think time is, when you stop trying to count it like a pile of laundry and start measuring it like a dimension of space, suddenly the equations work. Suddenly the universe makes sense. We are not done, because even if we accept that time is a dimension and that it stretches and squashes with speed, there is a much deeper question lurking at the bottom of the well. We talked about measuring time, and we talked about the arrow of disorder, but we haven't talked about the beginning. If time is a measure of change, what happens when you run the movie backward all the way to the first frame? If the universe is expanding and we wind it back, it gets smaller and smaller, hotter and hotter. Eventually, you hit a point where the laws of physics themselves start to melt. You see, all our clocks, our atoms, our planets, our light beams, they exist inside the universe. But if the universe itself was born in a moment we call the Big Bang, does it make sense to ask what happened before that? This is the ultimate test of your new definition of time. If time is just a way of ordering events inside the universe, then asking what happened before the universe might be as nonsensical as asking what is north of the North Pole. It sounds like a valid question grammatically, but geometrically it is gibberish. There is no north of the North Pole. There may be no time before time began. And yet we still have that nagging feeling, that internal counter, that voice counting 1, 2, 3. We desperately want the universe to have a backstory. We want a timeline that stretches back forever. It is hard to accept that the tape measure might just start, that the counting machine had an on switch. This creates a friction between our psychology and our cosmology. We are finite beings trying to comprehend the infinite, using tools made of meat and electricity. It is a wonder we understand anything at all. Consider the patterns again. The person who sees the tape measure in their head can count while reading because they are using different circuits, visual versus verbal. Physics is the same. Classical mechanics was the verbal counting. It worked for day-to-day stuff. Relativity is the visual tape measure. It allows us to process complex patterns that the old way couldn't handle. We are constantly upgrading our mental software to match the hardware of reality, and the upgrade process is painful. It requires discarding ideas we love, like the river of time. But here is the beautiful part. Even though your intuition is wrong, even though your internal clock is a biological hack, and even though time is a flexible, relative, bendy dimension rather than a strict metronome, it still works for you. You can still boil an egg, usually. You can still meet a friend for coffee at 2 p.m. The weirdness of relativity is hidden under the hood. You don't need to understand the combustion engine to drive the car, and you don't need to understand space-time metrics to live your life. But isn't it better to know? Isn't it better to know that the engine is there? This brings us back to that strange experiment with the counting. Remember the difference between the person who hears numbers and the person who sees them? This is not just a party trick. It reveals a terrifying gap in how we understand the universe. When two people talk to each other about something complex, like time or relativity or love, they think they are speaking the same language. They nod, they agree, they say, "I understand." But what is really happening? You are running a massive, invisible translation scheme. You take the words I say and convert them into your private internal imagery, which might be completely different from mine. I say 1 minute, and I see a clock face. You hear a voice saying 60 seconds. We arrive at the same answer, so we think we agree. But the machinery inside is totally alien. This matters for physics because it exposes the fragility of common sense. Common sense is just the collection of prejudices you acquired by age 18. It is built on your specific internal imagery. If your mental image of time is a tape with numbers on it, you will struggle to understand how time can bend. If your mental image is a voice counting, you will struggle to understand how time can be spatial. When we try to teach you about the quantum vacuum or the curvature of space-time, we aren't just giving you new facts. We are asking you to delete your operating system. We are asking you to throw away the tape measure and silence the voice. And that is why it feels so hard. That is why your brain rejects it. You aren't just learning, you are translating against the grain of your own biology. So let's try to break that biology one more time. We talked about how time slows down when you move, but there is a consequence of that which is even more disturbing. It destroys the concept of simultaneity. Imagine you have two very long poles, miles apart. You decide to flash a light on top of both poles at the exact same instant. Now, you see them flash together. Simple. But now, imagine a spaceship flying past you at half the speed of light. To the person in the spaceship, those flashes do not happen at the same time. They will measure, absolutely correctly, using perfect instruments, that one pole flashed before the other. Who is right? You or the spaceship?
You are both right. This is the part that breaks the human brain. We are obsessed with the idea of a universal now. We think that right now something is happening on Mars. But right now is not a physical reality. It is a coordinate choice. If you change your speed, you slice the loaf of space-time at a different angle. You literally change what events are considered simultaneous. This means there is no universal master clock ticking in the background of the cosmos. There is no God's eye view where everything happens in a neat sequence. The order of events can actually flip depending on how you move. Cause and effect usually stay safe, but the timing is up for grabs. If now is relative and time is just a dimension like space, this leads to a conclusion that makes the river of time look like a nursery rhyme. We call it the block. If time is a dimension, then the past, the present, and the future all exist simultaneously. Think of a movie reel. You watch the movie frame by frame, so it feels like a story unfolding. But if you hold the reel in your hand, the end of the movie exists at the same time as the beginning. The frames are all there, frozen in plastic. The only thing moving is the light of the projector. In this analogy, your consciousness is the light. The events of your life, your birth, your breakfast this morning, your death, they are all just frames on the reel. They already exist. They always have. This is why physicists sometimes say the flow of time is an illusion. We don't mean it's fake. We mean it's a perspective trick. The dinosaur that died 66 million years ago is not gone in the sense of being erased from reality. It is just at a different coordinate, down the road in the time dimension. Just because New York is far away from you now doesn't mean New York ceases to exist. It's just elsewhere. The past is just elsewhere in time. The future is elsewhere in the other direction. The structure is static. The experience is dynamic. Now, you might ask, if the future already exists, do I have free will? That is the wrong question. That is a philosopher's question. The physicist's question is, does the system allow for predictability? And the answer is messy. Remember the egg breaking? That's entropy.
The future is the direction of more mess. Even if the block is static, the patterns inside the block follow rules. You can't just jump to the end of the movie because the frames between here and there are the necessary steps to build that future. You are the process. You are not a passenger riding through time. You are the chemical reaction that is time. You are the shuffling of the deck. Let's go back to the counting experiment one last time because there is a hidden lesson there about capability. The person who could visualize the tape measure could do something the voice counter couldn't. He could read and count at the same time. He had a parallel processing power because his internal imagery was different. Physics gives you that power. When you stop translating the universe into rivers and flows and start seeing it as geometry, as math, as structure, you gain a superpower. You can see how black holes stop time. You can see how gravity is just the bending of the map. You stop being a victim of the illusion and start becoming a reader of the map. And yet, we must be humble. We talked about how we store information. Bessel functions, exponentials, electric fields. We learn these fancy terms, we write down these symbols, and we think we have captured reality. But remember, the guy next to you might be storing that same Bessel function using a completely different mental image. He might see a vibrating drumhead while you see a squiggly line. We are all just blind people touching an elephant, describing it to each other in languages we barely understand. The math work, that is always a translation. We found that simple counting to a minute is susceptible to all kinds of external factors and internal methods. If our sense of a mere 60 seconds is that unstable, imagine how unstable our sense of eternity or beginning. We ask, how did the universe begin? And we expect a story like, once upon a time. But the universe doesn't work in story. It works in states. It works in fields. It works in ways that might not even have a before. We are trying to count the socks of the universe, but the universe isn't wearing socks. It's weaving the fabric itself. So what is time? Time is the thing that stops everything from happening at once. Time is the heat death of the universe waiting to happen. Time is the curvature of space caused by matter. But most importantly, time is the mirror. It reflects the limitations of your own brain. When you look at a clock, you aren't seeing time. You are seeing a machine designed to comfort you. You are seeing a regulator for your society. Real time, physical time, is a wild, untamed beast that moves at different speeds, stops near black holes, and might not even flow at all. If this makes your head hurt, good. That means the translation scheme is breaking down. That means you are starting to see the cracks in the wall of common sense. Don't be afraid of the confusion. In science, confusion is not a dead end. It is the starting line. It means you are about to discard a comfortable lie for a difficult truth. Time is not what you think it is. It is so much more. And the fact that we, little biological machines made of stardust and anxiety, can figure this out, that is the greatest wonder of all.